Yeah, thank you all for coming. I hope you are still awake somehow. I'm super tired, so I'm sorry if I'm not moving around a lot today. So today, I want to talk to you about what I consider to be Rust's approach of getting things right. But first things first, my name is Pascal Hertleif. I'm currently involved in the DevTools team of the Rust project, so if you have ideas or issues with any tooling around Rust, please talk to me. Also, this year I've been managing the CLI Working Group, which currently is trying to make command line applications really easy to develop in Rust. If you've tried to write a command line application in Rust and had some ideas or issues there as well, please come talk to me too. On the internet, you can find me on these URLs. And with that, let's get right into it. So the talk's title is how Rust managed to get things right, which is pretty presumptuous. And, well, you may be asking yourself, what was I thinking? Like, how can this random dude on stage deliver a talk on how to actually write the perfect program? And, well, I'm sorry to disappoint, that's not why I'm here. I'm not going to give a very technical talk at all, and it's not going to contain any code. What I instead want to talk to you about is basically a bunch of cool projects and how they managed to become really ambitious projects that present the Rust community in a very good way. So, why give this talk now? Rust is still pretty young. Even though we just had like this big release of Rust 2018, and it seems like we have figured out what Rust is supposed to do and how good Rust code is supposed to look like, I'm pretty sure that we still have a lot to learn and a lot to gain from continuing to learn and discover new ideas. So, to go even one step further back, I want to ask, what is Rust? And previously on the Rust's website, it says it's a systems programming language that runs blazingly fast, prevents segfaults, and guarantees thread safety. You probably have read that at some point in your life and felt like, cool, really cool. Like, this is a bunch of cool features, but what does it actually do for me? The current version of the Rust website changes the slogan to be a bit in a different, going into a different direction. It right now says beneath the Rust logo, it's empowering everyone to build reliable and efficient software. This is less of a feature list, and it tells you how Rust helps you yourself. I really find this to be a very good way to describe what Rust is about. But as always in talks, you should not present 2 points. You should always go for like the trifecta of 3 points. And I asked, well, what is another interesting idea to describe Rust? And I went back to the past and looked at how the inventor of Rust first described what the programming language was about. And he said, Rust is technology from the past, come to save the future from itself. And you may be like, what? Like, what did Graydon even mean by that? Okay, fine. Surprisingly enough, he goes on in this email announcing this new programming language, and he said, like, well, there are a lot of older languages that do very cool stuff and newer languages that are more simplistic, and somehow we keep forgetting already learned lessons. And I felt like this is something I wanted to give a talk about. So I have this premise that the Rust community is really good at looking at prior art. And if you're not familiar with the phrase in English, prior art is, according to Wikipedia, all the information that has been made available to the public in any form before a given date that might be relevant to a patent's claim of originality. So it's from patent law, basically. Like, if you wanted to invent some new technology and had to prove to the patent office that this is actually original art, you had to also look at prior art. Okay, but luckily enough, we are dealing with software, and aside from some weird patent cases around software, we often have like access to cool research material, open source implementations, and a bunch of different ways to figure out how someone else tried to solve this problem we are looking at. And you may have heard of this quote by Picasso, who said, "Good artists copy, great artists steal." And luckily, like, stealing in software is very different from stealing in the real world, because you're not taking something away, you're only making a copy after all. Which is good, because we can improve everything and not just swap one thing for another. So we don't have to reinvent everything. We can check out existing ideas and try to come up with ways that they might make sense in our current new context. Because you might also feel familiar with this idea of some person on a team who looks at a problem and then they go away for some time and they show up a week later and say, "Okay, I've solved it." And you have no idea what happened. Like, apparently they sat down in some empty room and like figured it out all by themselves. And for some domain-specific problems, like if you have a very specific business case, this is a totally fine approach. It might even be the best approach, because after all, your business should try to do some original stuff. But there are a lot of general concepts we can actually try to improve. And for general concepts, it's a good idea to get rid of this approach of not looking sideways. We can oftentimes try to not say, "Okay, this is bad because it's not invented here," and say, "This is good because we know all the facts and all the projects around us." And also, this is not rewrite it in Rust talk, because you might be thinking, "Okay, fine, I've looked at this implementation here, and it's in C, so I rewrote the exact same thing in Rust, and now it's good." No, that's not what I'm saying either. It's supposed to be a talk where I'm convincing you to be curious and try out weird things, and I hope I managed to at least pique your interest in some of it. Okay, let's settle down and be actual and look at concrete issues. For example, you know that the borrow checker likes this concept of having ownership and borrows inside the type system. This is one of Rust's main selling points, because the problem it tries to solve is that we want to have high-performance code, but don't want to have memory safety issues. And most people, I think, have only ever been exposed to this concept of ownership and borrowing by Rust, but it's actually not Rust's own invention. In fact, there's also prior art for that. You might have seen in the description of this talk that I mentioned Cyclone. And Cyclone is actually an interesting language. Like, it's supposed to be a safe C, which has some interesting alternative pointer types. For example, pointers that are proven never to be null. And it tries this by doing region analysis. It's really interesting. It was developed at AT&T Labs in 2002, but looking at your faces, you've not heard of it. Why is that? Okay, another interesting weird language is ATS. This is one of those languages that is ML inspired. Like, if you've ever used OCaml, you know how it might behave. And the one thing that sets this language apart is that it had a built-in serial improver. Basically, the type system was made very, very powerful by actually being able to prove your programs. So it went all in and said, okay, if we have a type system that's powerful enough to prove like the absence of buffer overflows, we can have a safe programming language too. And funnily enough, it was really fast. Like, there are some simplistic benchmarks where it runs as fast as C. because all the checking is done at compile time, which is something that Rust also does. And I found this great quote from Philip Wadler, who is a professor of theoretical computer science at the University of Edinburgh. And he said, logicians usually get there before computer scientists. And that's funny because he is a computer scientist. And one other interesting field you could look at when thinking of this, where does the borrow checker come from, is affine logic. And the idea is like in the 50s or the 60s, people tried to figure out logic in the sense of what can we do with it. But in the 70s, they went a bit further. And this concept of linear logic was first presented. So just as a quick recap, regular programs don't restrict how many times you use a resource. Linear logic says, okay, you can use every resource exactly once. It's a bit hard to make a programming language where you can use things only once. So a weaker version of that is affine logic, which says, okay, it can't be used more than once. You can still forget stuff. And there's also relevant logic, just as a counterpoint, which says, okay, it must be used at least once. There's this symmetry. And people have been trying to figure out like how to make a programming language that uses these concepts from logic from like 40 or 50 years ago. And it is hard. One paper from 2000 presented this functional programming language called LambdaLa. And its main property was that there is a subset of it that is typed so that, and let me quote, polymorphic formulas of intuitionistic light affine logic are available. So basically, you can use affine logic to express programs in this language, but I'm not even able to really pronounce what the abstract is about. So maybe it's not as approachable as we want it to be. And that's basically the main point of the section. Like, Rust finally had this brilliant idea how to present all these concepts, or most of these concepts, in a way that is actually accessible to all of us. Like, we are sitting here because this is accessible. If this was still like LambdaLa, I'm pretty sure this room would not be this full. And also very interesting, it's not just about approachability, but it's also about adapting these concepts to the context we are in. Like, we need to make this work in a pragmatic way that solves our problems today. We want to have memory safety and high performance, and we want to have it right now rather than in 25 years. So one of the main issues with the first releases of Rust was that people said, okay, this is fine, this is an interesting type system, but I can basically come up with a program in 5 minutes, and the program is totally valid, and I can tell you how valid this actually is, and the compiler still rejects it. So the original implementation of this borrow checker system didn't understand all the valid programs. And it actually took us 3 years to finally land the next big iteration of these concepts. And this is basically the non-lexical lifetimes you may have heard about, and which are now enabled by default in the 2018 edition. But still, this is adapted for the current context and adapted for the usage patterns that have evolved in the last 3 years. But it's not the end, by far. Like, I still can show you programs where you're trying to borrow parts of a struct, and the compiler says, no, you can't, because another part is already borrowed mutably. Or where you're trying to have structs that reference parts of themselves. It's not easily expressible right now. Okay, this is quite theoretical, and you might be wondering, like, am I going to talk about compiler internals now? So I'm going to stop at this point and actually talk about a very pragmatic example, because there is a program called ripgrep, which is a super fast competitor to grep and Silver Surfer, AG. You may have heard of it, and if you've ever used Visual Studio Code editor, you've probably also used its search function, which is based on ripgrep. The main feature that sets this program apart from other implementations is that it uses regex crate instead of, for example, Perl-compatible regex expressions. It's been the same author, so that makes sense. But I had a look, and it's really interesting, like what needed to be done to make this highlight of Rust's accomplishments. So the prior art for the regex crate itself is the Pike VM, which is basically a description of how you use deterministic finite automatons to run regular expressions, very computer sciencey. But still, this wasn't enough. Like, this is one thing that grep also does, and it's fine. But it's not what makes it fast. What makes it fast is that it goes on and looks at other algorithms that have been discovered 50 years ago. For example, by Boyer and Moore and Aho and Korasik, who tried to come up with ideas on how to find matches on literals in strings very fast. And it goes on and also adds like a lazy finite state machine on top of the Pike VM to make it more memory efficient, because otherwise you could easily come up with a regular expression that is super slow. And then, most interesting to me was that it also includes an algorithm that is not available in any academic publication I have found, which is just called Teddy from Intel's Hyperscan project. And it uses SIMD instructions to speed up the substring matching even more. So the author of the regex crate, you may know the GitHub handle Burn Sushi. He looked at all these implementations and all these different approaches and tried to come up with a way to make them work. And what he did was bring it all together. This is why this is an amazing compilation of tools and why ripgrep is so popular. And also, like, when these ideas were first proposed, they were proposed to work on bytes. But actually, the world has changed a bit, and if you've ever used grep to search for an emoji, you might have seen that it actually doesn't really work, except if you pass like weird parameters to opt into another matching algorithm. So what the regex crate and ripgrep also do is support Unicode out of the box at no performance decrease. Basically, like, this is also just supported. So it works in 2018 as you expect it to. And also, it's highly concurrent, because it's still 2018 and we have multiple cores and want to use all of them. Okay, so far we've seen like two big examples, like this command line application and the Rust compiler. But you might also be wondering, like, okay, fine, am I going to talk about how to write ripgrep again? No. Actually, what I'm also trying to tell, except that it just adds on to the stuff I want to tell, is that you don't have to think big. You can just look at small, interesting pieces of code and wonder, can I make this better? And actually, if you look at the implementation of sort in the Rust standard library, the reason why it is like it is today is because Stjepan Glavina said, okay, this is a code. It's actually like really short, like 200 lines of code. And I'm pretty sure I can do better. Like, he looked at the sort implementation and said, yes, I can do better. And I talked to him, and it was quite interesting. It was not the story I wanted to talk to him about, but when he mentioned it, I was really curious. Because he said he was doing it just out of curiosity. There was no other reason, just he was wondering, how does it work, and maybe I can do better. And it's really, really powerful. And what he looked at was the current implementation, different versions of merge sort in other languages and standard libraries, block sort, which is also kind of a merge sort, tim sort, which worked similarly to merge sort, but not really. And just have a look at this pull request on the Rust standard library to see like a huge bunch of paragraphs just iterating on how which trade-off was made and why he looked at all these different implementations and what he actually settled on. Because what he settled on was pragmatism basically implemented in the way of cache efficiency, because this is how CPUs work today. If you have very efficient caches, you're probably really fast. Another very interesting approach to this is to look at the community side, because this story I just told is not just my story, but it's actually the story of how Stjepan first made a pull request to Rust. Like, he showed up and made this improvement to the sorting function just like that. It's not much code, but it's still like, if this is the first interaction with the community, it could go all the different ways. Like, he is changing the standard library. People might get upset. There might be trade-offs that no one knows about. There might just be no one there to review it. Actually, it took just 3 days to get this into the standard library. And this is super, super important, because if we as a community are transparent and open to change and looking at other people's work, we should also be open to looking at when other people propose changes to our work. And this is super good, because nowadays Stjepan is super active in the community, and basically the next thing he did was open an RFC to propose to add the sort unstable version to the standard of the sorting to the standard library, which is now available and also way, way faster than any other implementation I've seen so far. Okay, now I've presented 3 examples, and you might still be wondering, fine, what does it actually help me do now? And what I'm saying is, you should try to find inspiration for your problems in other fields, in other ecosystems, and see that there are a lot of people out there who are trying to solve similar problems, and maybe you can find inspiration there. So, other ecosystems. I've been iterating on Stjepan's story for a while now, and I'm actually going to tell it a bit longer, because one of the most interesting traits I have seen in the last year was that crossbeam channel has been really, really vamped up. Like, it's an improvement on the channels in the standard library, which is basically a multiple producer but single consumer channel system, which has for a long time had this unstable select macro to select over multiple channels, but it wasn't really powerful. And the idea with crossbeam channel was to basically put a very good alternative out there. Crossbeam channel is available in a bounded and unbounded way. It's a multiple producer, multiple consumer channel, and it has a very nice select macro. So what this enabled us to do is basically have a library implementation of what other languages have in their core language system. And that's not by accident, because this was developed by taking inspiration directly from what the Go developers have been doing for the last 8 years or so at that point. Basically, there was a very interesting design document from 2014 which iterates all the points that the Go developers looked at to come up with the design they chose. And the developers of Crossbeam Channel, among others, Stjepan, looked at this and could tell, okay, this is a trade-off we also want to do, and also decide, like, this is not something that fits into the Rust systems as it is right now. And the main idea was to avoid lock contention. And this sounds super easy, like, it's like 3 words that boils down why these channels are fast. Avoid lock contention. But it's very hard to get there, and this document was super helpful. And basically what we have right now is a fully featured implementation of a channel system in a library just sitting somewhere, and people can use it. Like, the language doesn't really block you in a way that you say, okay, I want to have this, but now I need to get knowledge of how the compiler works to make it happen. You can try and implement a lot of stuff just in a crate somewhere. And this is so powerful that there is talk about adding this to the standard library itself, because this is like happening years after the standard library implementation, and a lot of stuff has been learned in that time. Similarly, there is two more crates I want to talk about. The first one is parking lot, and the other one is hashbrown. So parking lot is a set of synchronization primitives as like mutexes and read-write logs, but it's implemented in user space. And it's also not a new invention. It's taken basically directly from the library that WebKit uses internally, which has a funny name, WTF, because it's a WebKit framework or web technology framework. I don't know, WTF. That's how I remember it. And the other one is hashbrown. So there was this talk a year ago at C++Conf from someone from Google who presented an alternative hash table implementation. And it turns out this thing called Swiss table is super, super efficient. It uses way less lookups and way less instructions for a key lookup than any other implementation I have seen, at least. And it works by using SIMD instructions and clever packaging in memory. And hashbrown is a Rust implementation of exactly this hash table. And there are two PRs open right now. The first one is about putting parking lot into the Rust standard library, and the other one is about replacing the current hash table we have in Rust standard library with hashbrown. And this is only possible because they work or can work as drop-in replacements. So a super powerful way to improve our language and ecosystem is to be able to come up with ways that we can just switch out and improve continuously over time. So these were all examples taken from other ecosystems, other languages, and other companies, basically. There's one other source of inspiration that's a bit more difficult to get into, and that is academia. Just a quick show of hands. How many of you studied something related to computer science? Okay, that's quite a lot, like 60%. And how many of you like reading academic papers? That's still a good number, not as many, but still a good number. And you've probably figured out somehow how to get into a paper and how to read papers and how to actually figure out where to get papers, but most people have not, which is quite sad. So this whole resource is locked away for them, or for some of you actually, I don't know. I talked to someone who had a very interesting point to make. Tyler Neely told me that so many awesome engineering projects are basically just out there. They can be pulled off by just taking a quick look at where the current research is at in a particular field, because often the implementations are lagging behind by several decades. So if you enjoy reading papers, one idea would be to just read more of those and try to implement the best ideas. And just because I didn't know how many of you had any academic background, and I still really don't, I wanted to also point out where to find some interesting papers. Because for me it was really, really hard to get into this mindset of actually doing that in my free time and finding stuff that was worth like spending half a day just trying to comprehend something. So two interesting resources I have are Papers We Love, which is just paperswelove.org, and the other one is an interesting blog, The Morning Paper. It's both about presenting papers that are somewhat approachable, but still weird enough that they are not like published in regular newspapers or on Hacker News. And just like my approach to reading papers is quite simplistic, actually. I try to read like the abstract, figure out is this something I could actually identify with, and is this interesting to anything that might be interesting to me, and then I read the conclusion, just to figure out if they have managed to do something of value. And that allows me to basically read everything Papers We Love or The Morning Paper publishes in like 2 minutes, and then sort out like 90%. But still, this is 90% papers I've now knowledge that they exist. And actually, I'm not alone, because I talked to Geoffrey Capri. You may know him from the NOM parsing library, and he told me like most of the things he reads have no useful application whatsoever for him. And the funny thing is, though, that he often finds himself years later looking back at what he read and says like, oh, I totally misjudged, or I totally didn't know what this could do for me then, but I do now. So can you act like a machine that just consumes research papers and spits out awesome Rust projects? Yeah, probably not. This is not how people or actually research work, but you can try to look at more sources of inspiration and try to look at it from a perspective of how can I make this more practical? Like, how can I actually apply this to my life? How can I, well, not your life, but probably your code or your work, I don't know, maybe also your life, if you're really passionate about it. You can ask yourself, can we reach just this bit more further? Is what we're doing right now actually the best approach, or is there someone out there who had like this brilliant idea and nobody really made it happen? Because I'm pretty sure that there is a lot of research that still just needs to be rediscovered. And this is a quote from Stjepan, as you can see, and he asked another question: can we bend the curve somewhere? Like, can we look at all the trade-offs that exist right now, and can we try to tweak them, like just a little bit? Is this enough? And this resonates with me as someone who has been in the Rust community for 4 years, because Rust is all about like overcoming these traditional trade-offs. Like you know this like crazy points of memory safety without garbage collection. It's happening, and stuff like abstraction without overheads. This is the selling points that we try to use to convince people to use Rust. And this bending the curve doesn't just have to be like language features. It can also be the implementation of weird but very useful other approaches. Like if we could just come up with some academic approach and putting it into like a non-intimidating version of itself. Like if we look at what the academic publication of the Swiss table hashing would look like, it'll probably be quite intimidating. Like the Robin Hood hashing paper was really, really good and really, really intimidating. And I know it because I walked, it took me like 2 years to actually get to the point where I tried to read it. And, well, it didn't really help me in my life so far. But it was interesting. And if I had been in this position 10 years earlier, I might have been the guy who actually sat down and said, wait a second, Rust needs a hashing, like a hash map implementation. I've seen this paper. I could sit down and actually try to make this usable. And basically the current hash map implementation of Rust is using Robin Hood hashing. So if we can make this weird other idea into a non-intimidating version of itself that's actually usable and package it in a way that's usable by Rust programmers, we have basically made a big contribution to what Rust programming looks like, because this is bending the curve somewhere. Okay, just one more story. This is about Greensrats, because not every story needs to have a happy end, right? In 2014, Rust had Greensrats, like something like Go routines or something like Node.js's event loop. It was actually using libuv, which is what Node used at the time too. And this allowed Rust to have async I/O. In 2014, it was actually quite good. At least it was usable. And they removed it. Like they went ahead and said like, yeah, we're not going to do it. which was way before Rust 1.0, but still like a very harsh decision. And why would they do that? Well, why would they look at an implementation that has async I/O, which is a problem that we are still in the process of figuring out today, and just remove a good implementation of it? And well, I'm not going to spoil Katarina's keynote. It's later today, but the idea why they removed it was not because it was the easy thing to do, but because they wanted to have the payoffs in the long run. They wanted to make the Rust team tried to figure out how to make more stuff work, how to have less trade-offs, because you can implement async I/O without Greensrats, and if you do so, you have no runtime and you can support embedded systems, which is a huge thing. And I'm pretty sure it's actually like going to be very okay. So it's okay to iterate on ideas. Actually, the first version of anything doesn't have to be perfect if you have the ability to say, okay, we are going to change it or upgrade it later on. It's okay if the first version is complicated, if you actually recognize that it's too complicated. It's okay if it's weird or not a good fit, if you recognize this. And it's also okay if it's not powerful enough, if you know what features you need to add to make it work. This is basically why Rust has so many unstable features that are labeled unstable, because they don't want to stabilize them right now, because they figure that they still know how to do it better, and they can't do it if they figure if they settle on a precise definition today. The ability that we can that we can change the implementation of hash tables today is a very, very good one. Like C++ can't really do this right now, even if they wanted to. Like Google's Swiss table is actually implemented in a C++ library, but it couldn't become the standard library because it's a totally different API, and it has to be a totally different API. So the first version must or may not be perfect, and that's totally okay. Because after all, Rust is maybe just this one thing where we can try to improve just the right aspects. Maybe Rust can be this, what Stepjan called, fertile ground for growing cool stuff. Maybe we can try to do very ambitious things. And to recap this talk at this point, and to come to some conclusion, I'm pretty sure that Rust is in a very good place right now. And we can do ambitious things. And to do so, I'm proposing 3 ideas. The first one is just to be curious, like to look behind the curtain, like to see there is an implementation of how slices can be sorted and figure out that we can do better. Maybe not sorting right now because it's very good, but some other aspect. And we should try to bend this curve of features and trade-offs. We should try to look at what's convenient right now and what's difficult, and try to just make one more difficult thing also convenient. And last but not least, we should also help other people discover awesome things. Like, I'm pretty sure I don't have time this year to do anything very ambitious, but maybe I just came across something that's really interesting and I can talk to you about it. And also, just to recap the other point, where to look for inspiration. The first one is other ecosystems of similar fields. Like, if you have an issue you want to solve right now, and you see there's a Java implementation, please don't say, oh, it's in Java, I'm not going to look at it. Please say, okay, interesting. They had probably like some time to come up with a solution, and apparently it works. I'm going to try to understand what they meant by it. And the second point was academia, and trying to see that there's a lot of research out there that has not been made accessible to the public, which is really sad. but also maybe some completely different areas. I'm not saying this is a solution for everything. I can't give you like this package deal of how to figure out cool stuff. You should try to find your own. Thank you very much.